Okay, so let's talk about part 3. All right? This is,
What? What just happened? What?
okay, so number 3 is both a conceptual problem and also an algebra problem. So here's going to be your setup. You're going to double stack 2 positive charges on one side, and then you're going to have a single negative charge 1 meter away. Okay? So what you're going to try and find is some point out in space where the electric field goes to 0. Now, remember, the only reason this can happen is because your electric fields are a vector quantity. So, also remember that electric fields are based upon a positive test charge. So, if I go out here and I put a positive test charge right here, what's it going to feel towards the negative charge?
Attraction.
Attraction.
Yeah.
What's it going to feel from the positive charge?
Repulsion.
Right? So basically what you're trying to find is that point out in space where the repulsion from the negative charge, excuse me, the repulsion from the positive charge is balancing out the attraction towards the negative charge. But this is double stacked, okay? Now, why don't I try to ask you to find that point to the right of the positive charges?
Because what you say?
Why didn't I set this problem up and ask you to try and find the point to the right of the positive charges where the electric field would go to 0?
So it's farther from the negative
There's 2
charge.
positive charges and there's 1 negative.
So what?
So it's farther
So
from the
the-
negative.
so the
negative
negative
charge
charge
is weaker, the positive
You
charge
have
is
to have the
stronger.
negative charge closer to counteract the strength of the positive.
Because one of the 2 factors that determine electric field.
Charge.
Charge and
Distance.
distance. So if this is 2q, that's just going to be
1.
q. So at that point, even as that distance increases, that repulsive charge is always going to be bigger from that positive charge than it is from the attraction towards that negative charge. But on the other side, you can compensate for that. You can say, okay, hey, I can put a positive test charge out here that can be closer to the negative charge that would compensate for the stronger repulsion from the 2 positive charges. Okay? I can't do it down here. I can't do it up above. The only chance that I have is going to be some point out there where that's going to effectively go to 0. All right. So, mathematically, I'm just going to get you started. Okay? So, mathematically, here's what you've got. So, you know the value of the electric field, right, is going to be KQ over
R squared.
R over R squared.
R squared.
R squared. Okay? So, you know this distance here is 1 meter. Okay? You know this point out here is some R. You can use X, you can use R, I don't care. I use R. It doesn't make any difference. Okay? So, if you pick a point out here algebraically, if you put a positive test charge here, what's it going to feel towards the negative? Which direction is that electric field going to point?
The right.
Right.
That's going to point that way because that positive test charge out there is going to feel an attractive force towards that electron or towards that negative charge. This point out here is going to feel repulsive because of the fact that you have 2 positive values. So what you're going to try and do is find that point mathematically where these 2 cancel each other out. Okay? Got that idea?
Right.
Okay? That's what we're trying. Now, you can do guess and check. Let's just say I just want to pick a number and try it. Okay? I'm just going to pick this. I'm going to pick 0.2 meters away from the negative charge. I'm just going to pick a number. Okay? Now, let's think through the algorithm, what you would do. Let's just say you pick a number of 0.2. So the value of that electric field from that negative charge, okay, would be K, and you can actually go through and calculate this. You have KQ, and that's going to be that 1 nanocoulomb charge, but you've got to put that as 1 times 10 to the negative 9. And then you're going to divide that by 0.2 meters squared. And you could get that number, okay? You could. You want to do guess and check like Brookcamp, it's a Friday, I am not in the mood for algebra, okay? Not in the mood for algebra. Well, let's do this out of curiosity. Somebody take K times 1 times 10 to the negative 9, otherwise known as 9, and divide that by 0.2 squared.
Oh, my calculator.
What'd you get?
225.
225.
Not
Right?
You get that.
Newtons per coulomb, right? Okay? Now,
That can't be right.
What's 0.2
Look, K is 9 times 10 to the 9 times 10 to the negative
What's
9, which is 9.
0.2 squared?
No, like, that's not the answer.
0.2.
No, but that.
We're only
Like,
gonna
that's
have
right.
I need the distance.
Like, that's not
Because E
trial
has
and error.
zero,
That's
right?
the error.
Now, how are you going to find the electric field from the two positive charges? That's going to be K, and then
2 times 10 to the
2 times 10 to the negative 9.
1.2.
But what distance are you going to have?
1.2.
1.2
You triple tongue.
squared, right? Because you got to add the 1 meter to it, okay? You got to add the 1 meter to it. So, somebody give me this number.
Once again, my calc is not out.
What'd you get?
12.5.
Negative 9.
12.5.
Wait, why is it
You're
1.2
just explaining
meters?
my sling.
I should
Your sling?
Okay.
My cool
Why is it
thing.
1.2 meters?
Huh?
Why is it 1.2 meters?
Because this point is going to, it's point, I picked a point, 0.2 meters from here, but this is 1 meter. So I got to use 1.2 meters for that distance. Okay? See that? So clearly, what's happened?
No,
Not
bueno.
the same.
No way.
No, mom is way.
So,
No, don't say that, Young.
do you think I need to move it further away or closer?
Probably further away.
Further away. For sure.
Because I need to make this number get
Small.
smaller, and I need to make this number get bigger. But you're dividing it by the distance squared, right? Okay. So now, from an algebra standpoint, okay, from an algebra standpoint, huh? So if you were to just calculate the value of that field, that would be K times Q1, and I'm just going to put that over R squared. Okay? That's it. I don't know what it is. I'm just going to call that R squared, right? Now, that has to equal the second field. So how am I going to calculate the second field?
I don't know.
K times
Over.
2Q.
R plus 1 squared.
No,
Now you're
I'm not doing a quadratic.
You don't have to. Oh, that was a bold-faced lie.
Yeah, that's what I'm doing.
I know. But I'm telling you, that was, I was saying when he goes, I don't want to have to do it, and I said, you don't have to, implying that. I'm not gonna hold
Oh,
that
like
against
he
you.
doesn't have to if he just wants to take it zero.
Yeah. Now, pay attention to how I want this answer. The answer, how I stated this, is I want that distance from, as measured from the negative charge. Okay? Not from the positive charge, the distance from the negative charge. So what you're going to do is you're going to go through and you're going to calculate that distance. Now, once you get that distance, how could you verify at the end of the day that the answer is right?
Plug it back in.
Play back.
Yeah, go back up here and do this calculation again. See if the two values add up. See if
Just
those.
look at it.
Huh? So, now, the whole point of this is you're going to have a theoretical value. Then you're going to, the beauty of this program is that you can go out and test it. Okay? You can grab that E-field sensor. Yes.
Is the keyword the Both positives
Plus
and
negative.
negatives.
No, the key one.
It really doesn't make any difference,
Oh,
okay? Because it's like almost like an absolute value kind of thing, okay? So then you're gonna actually test it, see if the field actually goes to zero. Then you're going to start to draw lines of equal potential. So in that big space down below on number 8, okay, you need to do two things. You need to sketch the equal potential lines, and then you need to draw in the electric field lines as well. Which direction are they pointing? Are they pointing away or are they pointing towards? You don't have to draw 1,000 of them, but you should at least have a pretty good representation of where the electric fields are, which direction they're pointing, and the same thing with the lines of equal potential. I would have at least 7 or 8 lines, and I'd probably have at least maybe 10 or 15 arrows showing the direction of the electric field. Okay? All right. Make that happen. Levy Pruitt.